Okay, so I was just talking about the neutron degeneracy pressure is what pushes back for a star, that is more than 1.4 times the mass of the sun, but less than 3 times the mass of the sun, and that kind of thing is what we call a neutron star. All right, so. And of course, the property of them rotating and the magnetic fields trapping charged particles, giving off radio pulses. That's why when it was originally known as a pulsar. Okay, let's see. Neutron stars are eventually expected to slow down to the point their emission becomes undetectable. That's who knows how long that's going to take. Anything else interesting? I mean, these are pretty minor things. All right, so we do observe these things all the time. All right, let's get to now. This idea of a gravitational wave was actually predicted by Einstein. So we're actually about to talk about Einstein and his. Let me just back up just a little bit. Isaac Newton gave us the equation for gravity, of course, and we use that equation all the time. Like we've been using it. We've been using it in combination of where you get that's part of where the modified version of Kepler's third law comes from, and it's also used in the escape velocity equation. It's not you're just kind of tangentially using Isaac Newton's theory of gravity there. You could write down the equation for it. We're not actually doing that in this class, but at any rate, Newton wrote this equation, for gravitation along, around 1666 or so. He made that discovery, and published it in the 1680s, along with a whole bunch of other things that really began physics. But about 200 years after that, in 1916, there was a guy living in Germany. His name happened to be Albert Einstein, and he came up with a whole new theory of gravity. Now, Einstein's theory of gravity is for smaller mass objects, like, for example, the sun or planets and so forth. Einstein's theory of gravity and Newton's theory of gravity are indistinguishable for really small masses. But when you get to really large mass objects, or if there's gravitation affecting something that's moving very quickly, then the distinction between Einstein's theory of gravitation, which is called the general theory of relativity, is more accurate. It's much more accurate, as a matter of fact, when you deal with more extreme circumstances that Newton had never thought of. And so when you have like really incredible masses, like a neutron star or two neutron stars, let's say, orbiting each other, it can create what are called gravitational waves. And we've actually been able to detect these very, very recently. We looked for them for a long, long time. There's a system called LIGO. That has been looking for these things, and so it's only been I think it's been less than 10 years since we discovered actual gravitational waves. All right, so then we get to black holes. Right, so let's say you have again massive stars. So just like a neutron star, a massive star, the end of the star's life, it explodes in a supernova explosion. And then the material, in fact, of course, during the supernova explosion, that's when the heavier elements, heavier than iron, are produced you know, on the periodic table. That's where all the heavier elements come from. But anyhow, if what is left long after the supernova explosion and the material escapes out, the stellar remnant escapes out into the universe, if what remains is more than 3 times the mass of the sun, then nothing. There's nothing that holds it up, right? Not electron degeneracy pressure, not neutron degeneracy pressure, nothing. And then what happens is the star collapses into itself, into a single point of infinite density. I know that's a strange thing, but we can actually deal with that mathematically. This equation right here is basically the escape velocity equation in a slightly different form. It's giving you this is called the Schwarzschild equation. Okay, so I'll do some examples. I'll do a video with some examples of this. It's actually a really simple equation. It does not use Einstein's theory of general relativity because it's a really difficult, very, very difficult mathematics, right? General theory of relativity deals with a subject called tensor calculus, which is extremely difficult. What's nice about this particular equation, Schwarzschild, who was a physicist who I think he died in World War I, and he actually came up with the size of a black hole, or the radius of a black hole, and it's a very simple equation that doesn't just uses Newton's theory, and which is perfectly fine. It tells you that the size of a black hole is equal to 2 times big G, which is the universal gravitational constant. That also appears in Einstein's general theory of relativity, by the way, times the mass of the object divided by the speed of light squared, where the speed of light turns out to be the escape velocity. Right, that's where this equation comes from. Again, it's called the Schwarzschild radius. So this is a really good example of what Einstein came up with as far as gravitation. So in Newton's formulation of gravity, gravity is just a force. Like a magnetism is a type of force. The electric force is a type of force. But what Einstein said is, no, it's not a force. What's going on with gravity is mass itself will warp, it'll change the shape of space and time. Right? Space and time are not, these immutable things anymore in Einstein's theory. And in fact, of course, this theory has been proven time and time again for more than 100 years now. And so really what's going on with black holes, let's look at this. Like if you had a waterbed, it doesn't have to be a waterbed, but that's a good example. Like a little baseball would just, curve a little bit of the bed around it, where like if you put a bowling ball and you had like a little marble or something, that would very much curve in other words, a baseball doesn't have as much gravity as a bowling ball. But then if you put a boulder on this, let's say if it's a waterbed, you can actually tear the waterbed. And that hole is the black hole, right? That's what we call, that's exactly where the name comes from. It's black because not even light can escape a black hole. All right, so this is what that equation that I said before is called the Schwarzschild radius. Well, like I said, I'll do some examples with that. In fact, Einstein's theory of general relativity was actually proven by an astronomer named Arthur Eddington back, I think it was in 1919. Or so. There was a total eclipse in Africa, or the total eclipse of the sun that occurred over the continent of Africa. And he actually took a trip there. And what Einstein's theory predicts is, even the sun, which is, far less massive than like, what a black hole would be, will deflect starlight. And so, since we've been looking at the stars for a very, very long time, we know exactly the positions of the stars with respect to each other. And so, if we looked at the, if you've ever been in a solar eclipse, which, like there was one back in 2017 crossing South Carolina and many other states, what happens is during the moment of the eclipse, it gets dark, and you can actually see the stars. Now, if you pick stars that are in the same direction as the sun, which of course you could never see during the daytime, those are the same stars that, sometime, several months later, the sun has set over the horizon, and so you can see those stars. So we know the positions. Anyhow, what Eddington did is he observed those stars and he looked for this deflection. And of course, it was predicted that the amount of the angle of the deflection was predicted because we know the mass of the sun. You could use Einstein's theory of general relativity to predict what this angle was, and it was in perfect agreement and has been ever since. And we've done this experiment many, many, many times over. All right, so let's talk a little bit about a black hole. So the black hole has a region called the event horizon. That's what the Schwarzschild, this thing here. I'm going back just a little bit. Sorry, did I already? Oh, jeez, sorry, I didn't mean to go back that far. The Schwarzschild radius. That's actually telling you the size of what's called the event horizon, right? So this is not a black hole, but the event horizon. Let's see. The event horizon is basically where, how far away from the center of the black hole does the escape velocity reach the speed of light? Like how, everything inside of the event horizon, the escape velocity for, let's say, a particle right here within. This is not a black hole, but let's say it was. If you had a particle right here, the escape velocity would be greater than the speed of light. And then if you get further and further from the center of the black hole, you reach a point where the escape velocity is just equal to the speed of light. And then just outside of this region, outside of the event horizon, it's a little bit less than the speed of light. So photons way over here could actually escape. All right. So and the center of a black hole. Let's see. The center of a black hole is called the singularity. Let's see. That should come up here. Center is singularity. No. Anyhow, here. Let me go backwards. All right. So the actual center is what's called singularity. Anyhow. That's the point of infinite density. Now the interesting thing about black holes is we can actually observe them. Not the black hole itself, but the material that is in orbit around the black hole. That's called the accretion disk. Some neutron stars will have accretion disks as well in binary systems, but a black hole doesn't have to have a binary system. It's just, out there in the universe all by itself, let's say. It can actually be in binary systems as well, but, so there can be an accretion disk, and that accretion disk, the material is going really, really fast, really close to the speed of light, and will actually emit X-rays. And those X-rays were first observed by this thing called Cygnus X1 in the 1970s, I think it was. These X-rays were discovered, and since that time, of course, we've measured the mass of it, and the mass is greater than 3 times the mass of the sun, and that was our first candidate for a black hole. Now, of course, there's been a lot more, hundreds and hundreds more since that time. All right. So